now we get to the final section here. The two beautiful theorems, Fatou's lemma and dominated convergence theorem. And I told you Fatou's lemma is like this type of theorem that you never know when to apply it unless somebody whispers in your ear that you should do it, and then some magic happens. And we're going to see that because we actually need Fatou's lemma to get to the dominated convergence theorem, which is easy to interpret. I will also give some examples at the end of today's lecture. But right, so this proof of the dominated convergence theorem is very somehow unexpected in my point of view. It's not very natural. Okay, so the statement reads, if I have just a sequence of functions fn and goes through all the natural numbers, then this is notation for lim-inf. Let me maybe write like this, more correct. So you remember lim-inf from last class probably? Yeah, so you take, let's write up what it is. So limit inf as n goes to infinity. Sometimes we write lim-inf, sometimes we write lim and make it a bar under. Lim sup is a bar above. Fn(x) is implicit here, so this is always pointwise. That is the limit as n goes to infinity of this infimum as k is greater than n, and then fk of x. So this is actually as a sequence in n, non-decreasing. Yeah, goes up. Why? Because every time I take an infimum of a smaller set, I get the same number or bigger. So this always exists. Remember, limit, we don't, existence is a problem, but lim-inf, lim-sup, they are great. They always exist. So here, yeah, it's hard to get your head around this statement. I mean, what does it really tell you? But anyways, an example whereby it doesn't hold would be like this. So take just on the real line with mu being equal to the Lebesgue measure. And then you consider your function, here's some point n, here's some point n plus 1. And you just take characteristic function of the interval from n to n plus 1. Now what is, if this is your fn, then your lim-inf fn is going to be equal to the identity 0 function, right? Because for every point x, this bump here is going to pass, and beyond that, when x is fixed, nothing happens. So this inf, this guy here, when n has become bigger than x, you just have zeros left. So it's 0, and then the limit of 0 is 0. Okay, so then we see that if we stick this in here, on the right-hand side we have 0, and on the left-hand side, on the left-hand side we have 0, on the right-hand side, so each integral will then be the number 1, and of course, 0 is less than or equal to 1. So why did I? Sorry, I'm getting tired. I thought I was working for a counterexample. Yeah, so this is an equation where you see that this can really be smaller than that. And now you also realize that it's very important here to deal with non-negative functions. Because if I flip this around, so I'll allow -1 here instead, then with the same analogy, I'm getting 0 here, but I'm getting -1 on this side. So non-negativity here is essential for this to hold. Okay, the proof, it's technical. I'll just write it up, all right? You think about it yourself and see if you can get a feeling for it. Okay, so this piece here, I'm just going to call that Gn. So this is then a non-decreasing sequence, goes up, and the limit is, you know, this fellow here, let's call him f. So then integral of f, the mu, by the monotone convergence theory. And here we have to be a bit thinky. So this is limit, then goes to infinity, integral infimum k bigger than or equal to n f k x d mu. Right, what happens when I move this infimum outside? Does it get bigger, smaller? Am I allowed to do that? Well, for each function fk with k bigger than n, my fk is bigger than this infimum, right? So this thing here is less than or equal to integral fk the mu for all k bigger than or equal to n. Now, if I take the infimum of a bunch of numbers, which are all bigger than or equal to some number, the infimum is still bigger than or equal to that number. So I can move this infimum to the outside, possibly making things bigger. I don't know why there's a parenthesis x here, actually. That's just a decoy. That's the Fatou's lemma there for you. But now, the grand masterpiece of this course is called dominated convergence theorem, one of the most useful theorems all time mathematics. Reads as follows. Okay, so the statement, it starts out with a function f and a sequence f1, f2, and so on, all defined on x. The values can be the extended real line or complex. So either or, this is not some funny notation with the complex line sitting on top of that. It's just either this or that. Okay. Okay, and now what we want to do is we want to say that if f is the limit of the fk's, at least almost everywhere, then the integral of f is the same as the limit of the fk's. Now, that's not always going to be true. Again, this example here proves it. Yeah? Because here, with this example, actually the limit exists of the n's, and that's identically 0. So we need some condition to ensure that when can we swap limit and integral signs in the general setting. And the condition is a bit obscure, or it takes some time to get used to. So what it says is that you should have some auxiliary function g, which sort of sits as an umbrella dominating the other guys, right? So, and a function g bigger than or equal to 0. So these guys not necessarily, but he, yes. Such that integral g the mu is less than infinity. Can be any number, can be 55 millions. Such that what? We need two conditions here. One, limit of fk as k goes to infinity is equal to f, not necessarily everywhere, just mu almost everywhere. 2, modulus fk is less than or equal to g. Again, mu almost everywhere, then the integral f d mu is equal to limit k goes to infinity integral fk d mu. Yeah. So f is the limit of those guys almost everywhere, so you can also see this as you're allowed to split the order of integration and limit here under this peculiar condition that there should exist some guy g with a finite integral. So somehow intuitively speaking, of course, there are many functions with a finite integral with all sorts of erratic behavior. But from an intuitive point of view, if you paint something, you know, okay, you could have a continuous function, even in the Riemann integral, that goes down to 0 and then it goes up, and then it's 0, 0, 0, and then it goes up again, right? So you know, having a finite integral doesn't mean that a continuous function necessarily, you know, goes down to 0 for big values of x. But at least in our mind, you can think of it like this, right? So this guy g, and think of it as something like this. So it sits on top of all the other guys, and it's some sort of roof, but it has these tails that goes down. And then if you think of an example like this one here, so you have your small train, there's no F3, then F4, F17 is over here, and so on, right? So it moves there. If this goes down to 0 sometime, it will hit the roof here, and this inequality is going to be violated. So just to exist, so this function g, we don't care about what it is. There are a million ways of how to engineer it when you need to test this condition. You just need to know that something like that exists, and then you're allowed to flip order here. So, but here at least we can see how it kind of prevents a situation like this simple example here. Okay. So the proof, the proof has an intelligent stage and a boring stage. The boring stage is just getting rid of these new almost everywhere statements. And yeah, so I do both for a change. So let's see how we can throw away this assumption and just assume that these two here happens everywhere instead of almost everywhere. But this is a recurring theme in this course, so this is the only time I'm going to explain it, okay? So what we're going to do is we're going to define a set E which contains all the crap that we don't want to deal with, and then say that E has measure 0, and we're going to use this result that if two functions are equal almost everywhere, their integrals are the same. That I proved like half an hour ago. So proof part 1. Put E to be equal to, well, what is unpleasant? Unpleasant is if g of x is equal to infinity, so we don't want to deal with that. Union, and then parentheses, and then we go union from k goes from 1 to infinity. What could also be unpleasant is if fk of x is bigger than gk, sorry, g of x. Okay, so here I need to write like this. Yeah, so these are the points where the second condition is violated. And then I need to also exclude the points where the first condition is violated. So union, parentheses, infinite union again. Sorry, there's no infinite union here. Okay. So this set has measure 0. Each of these sets have measure 0. And there's a countable union here, and this set has measure 0. Why do we know that? Well, because the g has a finite integral, and because of those boring propositions half an hour ago, we know that then g is finite almost everywhere. So all these sets have measure 0, and then the countable union of sets with measure 0 has measure 0. So E has measure 0. That is supposed to be written here. now you replace G with G times characteristic function of E, F with characteristic function of E times F, and the same with the F case. Now you see that we're dealing with functions. Everywhere something unpleasant happens, these guys are 0. And then, yeah, this is true, that is true. So on E, this is true, and that is true. So both on E and off E, both 1 and 2 is true. And moreover, the integral of this is equal to the integral of that. The integral of this is equal to the integral of that, and so on. So if we can prove what we want for these guys, we can then lift it to these fellows here, right? So like this, we can see that we can just say that, you know, we may as well assume that G is finite everywhere and that these two things hold everywhere. So I just wrote up what I said before. Part 2 of this argument now is where it gets nice. Yeah. So I usually try to highlight ideas behind proofs. Here I just must I must abdicate. I've never really figured out what's the idea behind this proof. F. Okay, we don't deal with the complex case that you sort out yourself. So I just deal with the real valued case, right? Right, so the functions, since G now is finite everywhere, also the F case are finite everywhere, and also F is finite everywhere, so we don't need to deal with it. So this is real valued, plus and minus infinity. We don't need to worry about it any longer. Okay, so they are real valued. What we're going to do is we're going to look at G plus F. Since G is bigger than modulus of F, G plus F is non-negative. Apply Fatou's theorem to that, get some inequality out of it. Then we do G minus F. Again, modulus F K is less than G, so it's a non-negative function. Apply Fatou's lemma, get some other inequality out of that. Fiddle around with these two inequalities, and bam, you're going to get the desired result. What goes on behind the scene? I don't know. So since F is equal to the limit now everywhere of Fk, k goes to infinity. You know, the lim-inf and the lim-sup are good when we don't know that he exists. But if he exists, lim-sup and lim-inf are always the same as the limit. Okay? Like the way of testing that a limit exists is to prove that the lim-sup and lim-inf exist and are the same. Okay, so we have this identity. And now let's work with integral f plus, sorry, g plus fk. No. So I'm going to work with the integral of g plus f the mu, which is the same as the integral g the mu plus the integral f the mu, right? By the addition rule that we established earlier today. And now here I write this as the lim-inf here. Okay, but then g for each point x, g of x is just a constant, so he can go in and out of the lim-inf. You know, can we, if we do plus a on the inside or plus a on the outside, it's all the same. So here we have now lim-inf. K goes to infinity. I'm going to stop writing this because k always goes to infinity. G plus fk, the mu, so there's a parenthesis there. Now Fatou's theorem lemma tells me that I can move this guy out and how, in a way that when the lim goes outside, it gets bigger. Remember always this, here is very easy to confuse yourself. Just remember that train, which is like 0 and then 1 and then 0 again. The limit from the inside is always 0. The limit from the outside is 1 or whatever, some positive number. So if you want to know which way this goes, think of that example. So then we have here lim inf on the outside. But now I can use addition again. So then I have lim inf integral g the mu plus integral f d mu k. Aha, but this is just a constant. Can go outside the lim inf. So now did that fit on the blackboard? Yes, it did. Okay, so we have one inequality in the middle, but look now at the beauty here. This guy and that guy goes away. So what do we have? We have at the end of the day that the integral f, the mu, is less than or equal to lim inf integral fk the mu. Now we are so lucky here that the lim inf, inf is small, sup is big. The lim inf happens to be on the bigger side of the inequality. Yeah? Usually you would expect it to be on the other end. And that's the beauty of this, right? So there's something clever going on here. Now we're going to play exactly the same game with, let's write it here. So we start out integral g the mu minus integral f the mu, and you do the whole chain here. So at some point you come here. So then you have, you have this with a minus. This corresponds to this step. Now this inequality goes the same way as before. So you get the lim inf. Let me write inf like this. And then, we go to the end. So we are here. So actually, so this guy pops out. And then I have plus lim inf minus integral fk the mu, right? Minus is still there. When you're dealing with inf, you cannot just take out the minus. Inf of minus a lot of number is the same as minus sup of the same bunch of numbers. Think through. So then I can do the minus, but now I have a lim sup integral fk the mu. So at the end of the day, we see that the lim sup integral fk the mu is less than or equal to integral f the mu less than or equal to limit inf integral fk the mu. But as you might expect, work it out yourself, the lim sup is always bigger than or equal to the lim inf. So these three guys must be the same. And then, okay, so now the lim sup is equal to the lim inf. But that in itself means that actually the limit exists and is equal to the same number. That's another, just No, this is just about sequences, yeah? So we're back to analysis 1, but it probably wasn't written out when you did your analysis 1 course. But yeah, so just sit down, work it out yourself. If the lim sup and the lim inf of a sequence of numbers exist, the limit must exist. That's like the squeeze theorem you need to use to see that. So the limit exists, not only exists, it equals the common value here. When equals 1 year equals all right, so where did it go, the theorem here? Yes, so there's more to it than just say that this one equals to that one, because once I've written up what I have here, it's not even clear that this limit exists. But that follows from the proof. So yeah, that should be underlined, that existence here is a non-trivial conclusion of the theory. Okay, I would like to go home now, but I want to also do some examples. I guess nobody feels pity for me except myself. But, no, all right, so I've said I've now kind of hyped this dominator convergence theorem to the skies. Let me then give you, round off this class with one example of, just to show you that this is actually quite powerful. So hopefully you remember some multivariable analysis class where you've been discussing when can I do differentiation of an integer. So if you have a function of 2 variables, you integrate in 1 variable. Now you have a function of 1 variable. Are you allowed to differentiate that guy? Well, of course, yeah. You can differentiate it, but are you allowed to move the derivative on the inside? Well, the question is, when is, let me write d dt, like we often use when we have a function of 1 variable. So if I integrate, if I have a function of 2 variables, I integrate with respect to 1, there's just a 1 variable function left. Okay, and I can also take the partial derivative of f, again a function of t and x, and integrate him. So we can ask ourselves when this is true, and hopefully I've seen theorems telling you when you're allowed to do this. Usually these theorems involve some sort of second order derivative here in t that needs to be bounded or whatever. So yeah, I'm going to give you the most general, or at least a very general version of this theorem, which just involves the first derivative. So in my whole life as a mathematician, I never needed anything more powerful than this. Now, of course, since we're in a more general setting, I can do the mu instead of dx. But then we get this, okay, so am I integrating now with respect to t or with respect to x? Well, to clarify such ambiguities, we can write like this. Yeah? So still t needs to be real, but the second coordinate can be anything. Okay, and yeah, we're kind of moving towards distribution theory if we're going to say that this derivative doesn't exist almost, but it exists almost everywhere and stuff like that. Let's just remove that. So we do where f of c dot x, so this means keep this as a variable, keep that one fixed, is c1, so we can differentiate. So let's just assume that this exists as a continuous function for every fixed x, yeah? So then the question is this true? And I think my condition here on my notes is maybe a bit different than the one in the book. So you need to check something to be allowed to do this. Most of the time this holds. It's kind of hard to construct examples where it doesn't hold, but I'm tired now. I want to go home. We just assume that these guys exist. I'm not going to write it up. So, given a point t0 and some epsilon bigger than 0. This is just what I'm going to do now. Okay, so we have here, here's our x. Here's my t-axis. I put t0. And if you think about what's going on here, I'm always integrating in the x direction. So I'm integrating like here, and then when you differentiate, you're interested in nearby points. So we integrate here, integrate here. Of course, I can integrate down here as well, but that's not so interesting. So what we're going to do is we're going to define like a strip where we have control. Okay? So this strip is going to have width plus minus epsilon. Okay, so I'm just interested in what goes on in that strip. And then I'm going to set g of x to be equal to the supremum t minus t0 less than epsilon of the t partial derivative here. This gives me for each x, I'm now for x here, I'm taking a supremum here, yeah, of the partial derivative. This gives me a function g of x. Well, usually this will be kind of impossible to compute, but of course you can take some other function g. Okay, let's write like this. So find a function g such that it's bigger than or equal to the supremum, yeah? And then we want this function g to be such that the integral of g, the mu, is finite. If we can find such a function g, then this formula is okay. We just write it like that. So, right. So here we connect with something else which is worthy of highlighting. So clearly I can now define, okay, let's do it like this. So, or maybe like this. Let's do like this instead. So t plus h comma x, and then we divide by h. So if I take a limit now of this, I'm getting the first partial derivative. I just realized while going through this that an alternative to doing what I do, check that the partial derivative is bounded in a strip, would be to take the function capital FH, which soon will reappear, and prove that, or demand that he is bounded, and then go ahead with the proof. And that's what they're doing here. So they have an example here, example 2.4.6, and essentially that's what they're doing there. So there's a slight difference. I think my version is much better. We're going to look at an example, a concrete example. Well, you know, shortly. So, and there you will see it's much easier to verify my condition than the corresponding one here, but both work just as fine, and the proof is basically the same. So what do we want to prove here with this new notation? I have that the left-hand side is equal to the integral of limit as h goes to 0, fh of x, the mu, On the right-hand side, by the same token, if I integrate this guy, what's going to happen is I'm integrating him, and I'm integrating him, and then the difference and divide by h. So actually, I'm getting this. So
the right-hand side is equal to limit as h goes to, sorry, h should go to 0. That's the whole point I want to highlight here.
okay, so left-hand side, right-hand side. This looks like an application of the dominated convergence theorem, because now what do I know here? Okay, this limit is just a function. Here I have many functions, but each one of them, as long as h is smaller than epsilon, each one of these guys is dominated by my g of x. Well, for that you need to also, okay, so the difference here at each x is bounded by this supremum. Why is that? It's the mean value theorem of calculus. So another exercise to work that out. So the limit each fhx is less than g of x. So for all h with modulus less than epsilon. Yeah, I'm being a bit sloppy as well. For all h such that modulus h is less than epsilon, but sometimes you just fed up with writing things. It gets too long, so I think this is understandable still. So it looks like we could apply dominated convergence theory, but we cannot, because this is a continuous parameter which continuously goes to 0, and technically dominated convergence theory deals with sequences that you enumerate 1, 2, 3, 4, 5. But this problem is not. So at the end of the day, we can apply the dominated convergence theorem also in these kind of settings. And to see how to do that, it requires a bit of thought, but it is not specific for this course. Maybe you've already encountered it in a calculus course or whatever, that it's the same kind of problem that, we say that a function is continuous at a point x if and only if the limit f of x as x goes to x0 is equal to f of x0. That's one definition of continuity. But then that happens if and only if the limit as k goes to infinity, f of x k is equal to f of x for all sequences xk, such that limit k goes to infinity, xk is equal to x. Yeah? And the way you prove these things is you argue by contradiction. I mean, if you have a statement like this, then clearly this follows. Yeah? If this does not hold, then you can always extract a sequence xk such that this is also violated. Yeah? So this is, this logical A implies B is the same as not A, not B implies not A, right? So we have proven that if this is true, then this is true. If this is not true, then this is not true. It means that they are equivalent. So in the same way, we can see here that the dominated convergence theorem applies in a situation like this, where h is a continuous parameter going to 0. The left-hand side is the limit on the inside, integral on the outside. The right-hand side is the limit on the outside, integral on the inside. As long as we have this dominating function g, we are good to go. And I am good to go home. Thank you for today, and see you next week. Just kidding. New day for me, same day for you. Let's move on. Okay, let's do a concrete example now of what we can do with this. So I'm gonna, first of all, I'm gonna write like this. Okay, so I'm introducing a function h of t, which I get by integrating. Technically here, okay, I should maybe write like this. So we have a set from 1 to infinity. I'm integrating over that set. So this is Lebesgue integral notation. We have a set down here. This was like putting a 1 here and infinity up here. Is like Riemann integral type notation. Okay, and now the question is, we want to compute h prime of t. Now, the problem is, of course, we don't even know yet how to compute h. And I'm not talking about the fact that maybe this integral is hard to find the primitive. Actually, it's not. So, of course. But what we haven't gone through yet is actually how to evaluate any sort of integral, because it's kind of implicit here that you do Lebesgue measure, you get the same integral as when you do Riemann integration. But I have never proven that, so we're not allowed to use any of the Riemann calculus rules to compute this integral. So that's the final section of today's class. I'm going to show that the Riemann integral and the Lebesgue integral coincide when you have Lebesgue measure here for integrable functions. And then we have to interpret the Riemann integral in this generalized sense. But I'll get back to that at the end of this class. So for now, let's just assume that this is true. So we assume that we can use this this identity. Here's the Riemann integral now. And then this one, we actually know what is the primitive. So this is the primitive. Now, what does it mean here to integrate from 1 to infinity? Well, technically, remember, we should actually put here some finite number r, and then let limit r goes to infinity be here. But then we see that this thing here is 0. So, I mean, the limit as r goes to infinity, that's why we need t bigger than 1. Then that limit becomes 0. So at the end of the day, we have minus, we get 0 minus x to the power of 1 minus t divided by 1 minus t. 1 to the power of that. So this is, yeah, good. So if we want to differentiate this, we can, of course, just do that. So then it becomes minus 1 over t minus 1 squared. Okay, but for many integrals, not this particular one, we have no, so Laplace and Fourier calculus are full of them, integrals over half axis or the full axis from minus infinity to plus infinity, then we can't really compute the primitive function, and we still want to differentiate them, right? So if they depend on two variables, we want to have some expression for the derivative, and then we want to do this differentiation inside. So what would that formula look like? Well, now, so this is my f of x and t. So I have to do the partial derivatives of this guy with respect to t. And how do we do that? Well, we write this as this, and then we see that this is minus ln x, and then just the same old thing, so 1 over x to the power of t. Okay, and then I want to differentiate this. So here's x, here's my t-axis, here's number 1. And I want to differentiate at some t, which is above 1. And then we had this strip, right, that I need to produce. But in this case, it's easy to see that, well, if I can control this guy for some t, it's automatically controlled for bigger t's, yeah? Because this is a decreasing function with t goes bigger. So it's in fact enough to choose some value t0 here, and then we can prove that this guy is bounded above by some integrable function for all t above that t0. So then we can differentiate or use this differentiation inside the integral for any t bigger than t0. T0 being arbitrarily would mean that we can do it for any t bigger than 1. Okay. Now, so first of all, is this even integrable? Yes, it is, because ln x goes very slowly to infinity. So you know there are these standard limits from calculus 1 saying that any power of x to any power goes faster to infinity than him, in the sense that the limit of the division is always 0. So let's do that. So for any fixed epsilon, this limit is 0. This is from analysis 1. But that doesn't really give me that I can integrate this, right? It's just the function just tells me that the function goes to 0. So how can this look like? So we start at 1, ln x is 0 at 1, and then x to the power of e goes slowly to 0, and this thing combined goes slowly to 0. So actually what we're integrating here is something like this, yeah? So it has a very slow decay to 0, depending on epsilon. Of course, if epsilon is high, then it goes faster to 0. So how can I say something about, how can I find this function g? Well, this is my t0 here. I'm actually going to create a gap here using 2 epsilon. Why is that? Because then, well, you will see. So now if t is bigger than t0, and this is equal to 1 plus 2 epsilon, let's say, then okay, this is what I wanted to arrive at. So now I have one function here, which the limit goes to 0, and since it's also continuous, I know that it's bounded. It's going to be bounded about by something, which I don't care what it is. Because the second guy here, thanks to this trick of splitting the gap there up in 2 epsilons, I have 1 plus something here, and that plus something allows me to conclude that this guy is integrable. If you want, with this new notation, we have that this is an L1 function, right? And this guy is bounded. So if you take a bounded function times an L1 function, you get again L1. Or another way of seeing it, you can just write this.
Okay, so that's my G.
Okay, so if I didn't know how to compute this explicitly, this would have been a potentially useful observation. Now, since it's just me making up stupid examples here, it's anyways, it's the same kind of calculations here that you would have gone through in a more difficult example. So I don't know, it was written on my paper here, that's why I showed it to you. Of course, it's an exercise that anyone can do to prove that actually this integral now becomes, where did I write it? This thing here, which you get by doing partial integration. Actually, do we? I'm confused. Let's find out. So switching over to Riemann integrals and doing partial integration, I'm getting here, before I had this is the derivative with respect to t, so now we have to be careful. Now the primitive with respect to x of, okay, so I write this, I have 1 minus ln x, that's my, so first function, and then I want to integrate like 1 divided by this. It's a function of x, and the primitive of that is, right? And now I'm going to integrate this guy against the derivative of him, so from 1 to infinity. Okay, so with the usual interpretation here, this is a limit, but he goes faster to 0 than he goes to infinity. So 1 minus t, we still have a negative exponent here. So we get 0 at this limit, and then when we insert 1, this guy is 0, so we again get 0. Here we have 2 minuses, so this is just going to be equal to this integral. And this one here and that other one is disappearing, so what we get in the end is integral this. This is starting to look good, right? Now the primitive of him, we already computed it once, is this guy, so now I can write that this is x to the 1 minus t divided by 1 minus t squared. Sorry. T is bigger than 1, so the upper guy disappears, and the final contribution is minus 1 over 1 minus t squared. Okay, so that was a bit instructive, so the formula is correct. Because the order of t and minus 1 doesn't matter because we have a square. Very nice. Okay, and if you were relying on the corresponding theorem in the book, we would have to consider like differences of 1 over x to the power of t minus 1 over x to the power of t prime or whatever some other variable, and somehow try to bound them from above. And I think it's easier to work with the partial derivatives. It's a matter of choice. Maybe sometimes one is more beneficial than the other. What do I know? But okay. So now, we have to clear up the connection with the Riemann integral for once. And we really see in this example that we need it. Because several times here, I had to resort to Riemann integration because we know how to integrate, right? We don't want to learn that all over. We just want to be able to apply it. We need theorems telling us when are we allowed to use Riemann integration and what are the possible pitfalls. There are pitfalls. So while editing this, I realized that the lectures were getting too long. I was squeezing in too much in the. So to make it easier, like I think around 50 minutes, 1 hour is a good size online lecture. So I cut it here, and we do the Riemann integral in a separate lecture next time. We will also talk about bits and pieces from. 2.6 is a section with assorted stuff, primarily complex integration of complex valued functions, and yeah, a bit about construction of new measures from old ones and stuff like that. With that, yeah, thank you for today, and see you next time.